very quickly, any questions about the assignment? Yeah, one.
Sir.
I said what? The solutions for? Yeah. Yeah. Oops. All right. You're saying that the link closed at the same time as the HackerRank was due? All right, that was a mistake. I can reopen it for today. You won't be able to submit to HackerRank, but you can always, you'll be able to upload your grade. Yes. Another. Boy, you always have these weird hypotheticals. Well, let's say for argument's sake, if your grade is missing, then it's your fault. But you can come and tell me about it. If when I publish a grade, you see your grade missing, let me know, because that's what the consequence of doing that is. Somebody had hold on. Online, somebody had a question? All right, go ahead. Yeah, no, that's a great question. All right, so there's an issue. If you use the built-in library heap queue to implement your heaps, apparently it runs much faster than if you do it yourself. Now, some of that could be just naivete in how you implement your heap. But I think that I have a feeling that, so there's two things, right? Probably if I took a look at your code, I could probably tell you a few things that you could have done to make it go a little faster. But would it necessarily go as fast as the library implementation? Probably not. And part of that, I think, is that, I think the standard library gets compiled at the C level. Now, I may be wrong about that, but once it's in the standard library, so even though you may load it as a module, it probably, it would benefit from those possibilities because it's there, right? But I can't guarantee you that's actually what's going on. It may very well be other things. The library itself may have been optimized, meaning, and then when they compile it, then they probably turn up the optimization level so that it punches a lot of the function calls that are to the same package. But to be honest with you, that's unlikely. That's actually unlikely, even though it's possible. The most likely, my most likely hypothesis is that some of that code is precompiled at the C level, and then they're making calls into that. Now, if I were to take a look at your code, a couple pointers that I could give you, and this is useful for going forward when you go build your own data structures, because as you realize, more and more now the assignments are going to require data structures. So a couple things. If you can turn references to links into array references, you'll benefit. But that's not always possible because sometimes you're dealing with a dynamic data structure that needs to grow dynamically that you don't want to have to copy a table out for, because then that's more advanced stuff, how to do that properly. But like, for example, a heap, you wouldn't want to implement a heap using your classic linked structure for a binary tree. That's just going to take you about twice as much time. Now, bear in mind, this is actually really useful for this course, I think, in my opinion, these lessons, because at one level, we're talking about analyzing algorithms so that you get orders of growth improvement. And there's definitely a difference between a log n time algorithm and an order n time algorithm. And hopefully you've seen some of that already. But now you're beginning to see on these things how, you implement your own heap, you use heap queue built in. The two of them are heaps, the order of growth is the same, but the actual time is different. And why is it different? It's because the constant that's embedded in the order of growth is what's drastically different. If you remember, Python is an interpreted language. So for every instruction that you write, if you happen to write it in a non-Pythonic way, it means that you get the full brunt of the interpreter. If you happen to write it slightly Pythonic, so for example, instead of iterating over indexes, suppose you want to iterate over the elements in an array. If you write a loop, so let's say the array is called LST, LST. If you write it as for I in range len LST, do something with LST square bracket I, your code will run about 1.5 times slower than if you write for V in LST, do something with V. Okay? Big difference, huge difference between the two. And you might say, what? That's the same if you write in C, that's exactly what you should do. If you write in Java, you should iterate over the indexes. If you write it in Python, the problem is when you iterate over those indexes, because Python's numbers it's called arbitrary precision arithmetic, means that if you calculate factor out of 1,000, you don't get the overflow error. You just get the answer. Well, that lovely convenience comes at a price. And the price is that every time you add a number, add two numbers together, it has to check whether it got an overflow. And if it got an overflow, it needs to change representation. Okay? So there's a whole bunch of safety checks that have to happen when you do ordinary arithmetic operations. So for example, when you say for I in range, you're just now in, so those i's are now going to increase by 1 each time. And subsequently, so every time it adds 1, of course, it has to go through that check. And then when you access the array at index I, how do you think an array access works? The base address, you know, the size of the storage location, multiply that by the index, add it to the base address, make sure it's not out of bounds, then go access it. So every time when you write LST square bracket I, that's happening every time inside that loop. When you say for V in list, you know what happens? It says, oh, let me find where list starts. What's the size of this? Oh, 4 bytes at a time? Okay, no problem. In C, it sets up a little counter that's going to stride by 4 bytes and just read off that word and store it in V. So what may have been 50 instructions just reduced to like 4 when you do that, which is why iterating like that can be much faster. So there's a lesson to be learned about trying to write it Pythonically. Second point is that if you can, and I hate to say this because it makes for bad design, but it's good to have known this. Basically, function calls can be expensive, right? So function calls in any language can be expensive. What that means, though, is that I don't want you to go around avoiding writing functions because functions make code readable. And in the real world, readability often trumps performance. There's only very few things that actually requires you to really crunch the performance to the point where you spend a lot of effort in getting it done at the expense of the code. In other words, it's very rare that you'll sacrifice readability in the interest or on the altar of performance. Okay? Most companies will reject your code for doing that because if it's unmaintainable, it's no good to them going forward in the future. So if it's fast today and then the next guy who comes along to maintain it can't do it and then they re-implement it and it becomes slow. Next, it's actually bad. It's bad for everybody. So if it's fast, it needs to be readable. And so part of the problem is if you start cutting out functions in the interest of trying to make it fast, likely going to make the code look bad. Now, a couple of things though. If you have a function because you need it to be recursive, check. Is it a tail recursive call? Because if it's a tail recursive call and speed matters to you, you might as well use a while loop. If it's not a tail recursive call, leave it alone, because that's probably the right thing you're doing. But maybe if speed really matters to you, then you might want to look at, you know, the usual techniques of dynamic programming and so on. So, but that's a slightly different thing, because dynamic programming is really going to take advantage of the fact that you're doing the same thing over and over for different contexts. Okay, so those two things you can keep in mind. Function calls are expensive, so but you still want to design with functions. Just want to try and keep them out of tight inner loops, for example, if you can avoid that. Tail recursive function calls, probably better to replace that with a while loop. And if you're iterating with a for, remember to use a Pythonic iterator rather than iterating over the indexes. All right? And then, of course, there's a whole bunch of libraries that actually do a lot of neat things for you. I don't like to promise these things, but maybe at some point, I will release a short list of packages where you can go look for some useful. In fact, I can tell you some of them now. So So you can go look up these for handy features. One is called iter tools, and the other one is called collections. And of course, if you end up having to use heaps, heap queue is a nice one. It's kind of limited, it only does minimizing heaps, so you have to kind of do some gymnastics to make it work for you. Yes? Oh, sorry? Right. Right, they weren't constant. Okay, so today we're starting a new topic, a new set of topics. Sorting. And the problem of sorting, let me just generically describe this. Yes. Yeah, so the only thing that I didn't really talk about in depth in terms of hashing, to go back, was properties of the function, the hash function itself and how it interplays with the size of the table. And to be honest with you, some of that requires you to know some modular arithmetic knowledge, which not covered in discrete maths, it's not covered anywhere. Geez, maybe I should have mentioned something. You think you'll survive in the tutorial? So, it's interesting. So you think I should insert a topic? Because that topic is not explicitly covered in this course neither. Modular arithmetic. It's not part of the syllabus. But you think I should include something on it? Would you like me to do it? No. I could defer this. I don't know if that's actually useful to you. No, I mean, I don't know useful to you. I know you want to know, but so a couple of things. And on the spot decision, hijack the lecture. I don't know. Actually, I'll leave it up to, I can in half an hour cover the bare essentials of what you need to know for modular arithmetic. But I don't know what your position might be if you'd feel really upset that I'm not following the syllabus anymore. In other words, if you know this already and you don't think it's necessary, then fine. And by the way, it's a peripheral subject. It's useful for understanding those hash functions a little bit, but and it's really useful generically for computer science, but it's nowhere in our syllabus, so it would be an optional thing, obviously. Yeah, it's not assessed in the only assessment of it is, like, for example, when I ask you, is a hash function good? Which is the kind of questions you have in the tutorial. So it helps to the understanding of that, but you're not going to be assessed on modular arithmetic. So quick vote. Should I hijack the lecture or go press on with sorting? Hijack? 1, 2, 3, 4, 5, 6, 7, 8. Press on with sorting. I thought I heard lots of people saying do hijack. I only saw like 8 votes for hijack. Press on with sorting. Nobody. Okay. All right, fine. Hijack it is. All right, no problem. We won't run out of time, so that's not an issue. We'll have time to do it all. I just, fine. So very quickly then, modular arithmetic. And then what I'm going to do is just give you a kind of brief. All right, so here's some definitions. And then this notion of inverses. I don't even think I need to get into Euler phi function. All right, maybe that's what we'll have time for, and then I'll give you a sense of how this is connected. So one of the things I wanted to keep in mind is, remember, your hash functions generally say do something mod m, m being the size of the table. And so why we want to look at this is to understand how those addresses, how that mod m plays in with the arithmetic that you're doing on the function. Okay, that's my point. That's why we're doing this. Okay? So a couple things. So first of all, let's just quickly put on some definitions. So this set here is to be understood to mean the set of integers. Well, if you think of it as, this is the set of integers that are between x and m minus 1. But it's also to be understood as an equivalence class. You guys remember from your COMP2211. All right, under the relation, if I took any integer and I asked what's the remainder, so Zm is the set of all possible remainders when dividing by m. Pens are frustrated. All right, so for example, Z5 is 0, 1, 2, 3, 4. And you can see that if you were to divide any number by 5, the remainder has to be either 0, 1, 2, 3, or 4. Okay? The reason it's considered an equivalence class is that I can consider, suppose I take any integer and I divide by 5 and I ask what is the remainder of that, I will always get one of these numbers. And so then you can think of these numbers as actually representing a whole family of integers. Okay? So we can think of Zm as being an equivalence class equivalence class obtained from a relation defined on integers by, we'll say x. So for any integers x and y, we'd say x r y. You've seen this notation, right? X is related to y. Let me write it as one line. For any x, y in integers, x r y, if and only if x minus y mod m is equal to 0. In other words, that is that x mod m is exactly equal to y mod m. Okay? And so then the point of this is that, well, you know that the only possible numbers mod m is 0 to m minus 1. And so then that single number represents a whole family of actual integers. Okay? So, there's a question online?
Yes, we can't see the bottom of the board.
Can't see the bottom of the board?
Yeah.
Soon.
All right, thank you.
All right, so example, so 0 is equivalent set like this. The representative for, I should say it's 0 in Zm. Or, okay, let's work with fixed number. Example, 0 in Z5 is a representative for all these numbers. There's 0 in there, there's 5 in there, there's 10, 15, 20, etc. Okay? Now, part of the reason why this is important is that ordinary arithmetic works just in the same in this set. That set for mathematicians is called a ring. If I take that set Zm and I consider it with an operation, well, it's actually considered a ring because it works just like how addition works over things like reals and integers, numbers that you're more familiar with. And to explain that, notice that if I took any two numbers in that class and added them, I would still end up with a multiple of 5. Multiples of 5 are those that have a remainder of 0. Yes? Yes? Okay. If I took any two numbers, so 1 in Z5 is maps to the set. What do you think? 1, 6, 11, 16, 21. And of course, the negative numbers are in there too, you know. Okay? Let's put a couple negative numbers in there just to make sure that y'all can see that. Give me some negative numbers in here. -4. Why -4? What's the remainder of -4 when you divide by 5?
I will try. Mommy.
What's the remainder of -4 when you divide by 5? -4, right? Okay. Would you agree? Would you agree that if I were to add m, so notice the relationship here. What's true about all these numbers? Or if you want to focus on the original relation here, the difference must be equal to m. In this case, because we work in mod 5, the difference is 5. So any two elements in the same set must have the same difference. So if I'm going to put a negative number in there, maybe that helps you to clarify it a little bit. What negative number could I put in here? It has to be 5 less than 1, which is what minus 4 is. Yeah? Or 5 less than minus 4, so minus 9. Or what else? Minus 14, and so on. Okay, now here's what's neat and true about this. Arithmetic is almost the same as you would expect if you're just working with strict integers. So for example, under addition, if I wanted to ask, so now I'm talking about arithmetic in ZM in general. If I'm doing addition and I do, so let's say, so for any x and y in ZM, right? X plus y is going to be congruent. This is how we say it now. We say it's congruent to. This is what we mean by when we're operating in the set. It's congruent to if I'd added in the integers and then reduced, find the remainder by that m. Let's check. So for example, in Z5, if I wanted to add, if I add 1 and 0, so it's that easy. 0 plus 1 is just 1. What I really is saying is that if you were to take any two elements from these two sets and add them, the remainder would be 1. You can check that. 16 and 5 is 21, and the remainder 21 when you divide by 5 is 1. Or if you don't like it because 5 was a special, 16 and 20 is 36. If you divide 36 by 5, you get a remainder of 1. Okay, let's do one that's less trivial. Something like 1 plus 2 is going to give you 3. What that really means is that anything mod 5 that's in the congruence class 1, or equivalence class 1, added to anything in equivalence class 2, is going to give me something in equivalence class 3. You can check that. Pick something from equivalence class of 1. 6, pick something in equivalence class of 2. Okay, 7. 6 and 7, 13. After you divide by 5, the remainder will be 3. Yep, you get 3. But here's where things get interesting. What if you took something like 4 plus 3? Now, working mod 5, this is how we write it. When you use a congruence sign, then you write the class you're working with. Sorry, the modulus you're working with. What do you think 4 plus 3 should be? Yeah, because 4 plus 3 in integers would be 7, and after reducing mod 5, you get 2. Now you can check that. Pick a number in the equivalence class for 4. 9, okay, and pick something in 3. Okay, 9 and 8, 17. 17 and 17 mod 5 is 2, right? So you actually do get 2. So interestingly, the arithmetic is working out even though the set is finite, and it essentially wraps around. That's how you can think of it. So that when you kind of overflow beyond this 5, you need to wrap around. So 5 maps back to 0, so anything that adds up to 5 is really adding to 0, adding up to 0. And so this is exceeding 5 by 2, and that's why you can think of it that way. It's in equivalence class 2. Arithmetic, so addition, works like that. Multiplication also works similarly. Subtraction, what do you think happens with subtraction? So for multiplication, it's the same. So x times y is going to be equivalent to the product xy mod m, reduced mod m. So for example, in Z5, if I do 3 times 4, what do you think I get? I get 2. And you can check that. Take a number mod 3. That's equivalent to 3, to 8. Take a number that's equivalent to 4. Okay. Or 19, or now you have to multiply 8 times 19. When I want to keep it small, you make it big. But all right, what's 8 times 19? 160 minus 8, right? That's 152. Okay. And 152 mod 5 will be 2. Yes? Okay, so addition and multiplication work just like you'd expect once you remember to reduce mod the number. What happens when we want to contemplate subtraction? Well, to really understand how subtraction and in fact division are going to work, we have to remember that subtraction is really the addition of the additive inverse of a number. So we have to remember that x minus y is really x plus the negative of y. So let's try and understand that. What's the additive inverse of, okay, so let me put it like this. For any x in Zm, negative x is going to be congruent to, what do you think? Going to be congruent to m minus x mod m. Does that make sense? If I'm working mod m, what equivalence class does m map to? 0. Exactly. So m is equivalent to 0 mod m. So therefore, if I add 0 to anything, I should get back that thing. Yes? So I'm really adding 0 to negative x here, as far as you're concerned. But when I'm going to work in the integers, that will be useful. So for example, in Z5, negative 4 is really equivalent to 5 minus 4, which is actually equivalent to 1. That makes sense? And we saw that when we were enumerating the set for equivalence class 1. Question? I added 0 to both sides. So I have negative x. I'm trying to understand what is negative x. And the principle is m corresponds to 0. So you can add m anywhere and don't change the value. You won't change equivalence class. Because when you add m to any member, you're getting another member of the same class, same set. So therefore, what we're really trying to understand, so the right way to think about this is that we essentially have divided all the integers into, let's concretely work with 5, m equal 5. When m equal 5, I've divided all integers, it's infinitely many integers. I've divided them up into 5 classes, 5 sets. And those sets have something in common. That's what this relation is. They basically differ by some multiple of m. That's what they have in common. What that really translates to is that if I were to divide by m and get the remainder, that tells me that gives you one of the members in that set. Now the idea is that I have all integers in 5 sets. What I really want to do is just pick a representative, and then that number represents the whole set. And so that's why 0 stands for all these numbers. 1 stands for all these numbers. And what I was pointing out is that there are negative numbers in here as well. Because you can freely add any number of m's to any element in there, and you get another element in the same set. Okay? So when we're trying to understand negative, what we're really trying to ask ourselves is, which of the positives from 0 or non-negatives from 0 to m minus 1 do we get when we add sufficiently m's to the original value? When I'm trying to understand which of, so remember Zm, I said over here, these don't have any negative numbers in there. So when I'm trying to understand which of these should map to a given negative number, what I'm asking is, how many times, when I add m sufficiently many times, I'm supposed to get one of those. Which one do I get? That's the one that's equivalent to the negative number I have. Okay? And what this does, it allows me to do that. Because this says negative x for any x is equivalent to m minus x. In fact, I could have, well, it's okay. If I wanted to do it for all integers, I'd want to use this rule. This is really what I'm pointing at. The difference between any two numbers in the same set in the equivalence class is going to be the modulus that I'm working with. All right, so negative 4 is equivalent to 1. Let's do another one. What's the equivalent to negative 2? Three. Okay, now things get really interesting when we have to contemplate division. Because division, what's the... So for division, so now we've dealt with subtraction, but what happens when we have to do division? Sorry? So if you want to do x divided by y, what that really means is you're really trying to multiply x by the inverse of y. That's, in general, what that means. And so now, if I ask you, what's the meaning of this y inverse? Now, if you're in prep school, you'd say it's a reciprocal of y. But the reason that they told you that is really the true meaning of an inverse, a multiplicative inverse, is it is that number that when you multiply by y, you get 1. That's what reciprocal is, right? Reciprocal of x is 1 over x. The reason for that is that when you multiply x by 1 over x, you get 1. So the real true meaning of an inverse, so the multiplicative inverse, which in this case I've labeled y inverse. Here, I'm going to use the word, so I'll use the word and then write the symbol. Multiplicative inverse, it's really important. So let me put it up here. The multiplicative inverse of y, that's written y inverse, is the number, let me call it z, such that z times y is 1. Because by definition, what we want is that y inverse times y is 1. That make sense? We're trying to define what y inverse is. We want it to mean 1 over y, but we can't do over because we don't have fractions, pure integers we're dealing with. So what I really want is that number when you multiply by the number I'm trying to invert, I should get back 1. Now let's try and understand this. For example, in Z5, what do you think 3 inverse is? Can you find a number that when you multiply by 3, it's equivalent to 1? Mod 5. So remember that all the numbers in 1 mod 5 are 1, 6, 11, 16, 21, etc. Can you find a number that if you multiply by 3, you get one of these? Yeah, because 2, 3, 6. So 3 inverse is 2. Because 2 times 3 is 6, which is 1 mod 5. Okay? This is mod M. Let me stick it in there because now that's really important because sometimes this might not be possible. Notice what this says, that when you multiply z and y, you're going to get a remainder of 1 after dividing by m. That tells you immediately that z and y can't be factors of m. That makes sense? If z and y were factors of m, there's no way you could multiply by another number and get a remainder of 1. All right. Importantly, in order for y inverse to exist in Zm, y and m must be relatively prime. What does that mean? Sorry? Two numbers are relatively prime. If they don't have any factors in common apart from 1, right? Are relatively prime if the GCD of x and y is equal to 1. So that's what it means to so let's go back. Let's wrap this up. I have to go back in. All right. So to wrap this up, hope the recording will still be there. Okay. To bring this back to the hashing story. Do you remember during the probe? Remember that we have this f dash of k and I is f of k plus g of I in general? It's not clear? And if g, so let's take, for example, when g of I in linear probing was just ai. And then in that case, you have, remember that this is all mod m. M being size of the table. So if I asked you, what kind of A do you want to choose? What kind of A should you choose that will ensure that you visit all possible locations before starting to revisit them? Well, 1 is one example. Can you do it in general? So that's right. Anything in the equivalence class of 1 would work just fine. Okay, but we have something even more general than that. Because the equivalence class of 1 is the smallest number in there. The next one bigger than that is m plus 1. It kind of is obvious, don't bother using any number bigger than m, since you're modding this by m. But there are other values of A which would be just fine. M minus 1 would be fine too, yes. In general, any of them that have a GCD of 1. Okay? Now, the reason for that and the proof for that is that it would be well beyond what I could do in half an hour if I'm starting from scratch. But the point is that out of this kind of arithmetic and out of this kind of reasoning about what the inverse means, one of the upshots is you'd want to choose, A such that the GCD of A and M is equal to 1. Now, obviously, if M itself is prime, if M is a prime number, then all choices except the 0 will be good. Because prime numbers don't have any factors in common with anything. Right? Yes? Okay. If M is something like a power of 2, then you'd want to choose A to be something that's not a multiple of 2. Not an even number. And that's what will allow you to visit all the possible locations. Part of what I would, so since I went into the trouble of giving you this, I actually had a question that I was falling back on because you didn't have enough knowledge. Now you have it. So maybe next week I'll release. Keep this in mind. So I'll see you tomorrow. Tomorrow we'll do sorting.